Okay, guys, in this video lesson, we're going to talk about the first law of thermodynamics and how it applies to conservation of energy. Okay, so first thing we want to realize is that the first law of thermodynamics is really an extension of our general law of conservation of energy, which tells us that in any chemical or physical process, energy cannot be created or destroyed, it has to be conserved. So when we're dealing with the first law of thermodynamics, we're focusing on this physical process of energy transfer, okay? And in energy transfer, we must be able to conserve that energy, all right? So equation-wise, what that tells us then is that any energy that one thing gains has to be equal to the energy that is lost by something else. Now, one thing we want to have here is a closed insulated system. So we want to be able to track energy change for two specific things without having energy loss to our environment. Now, the way we do that is through some sort of thermal insulation. Coffee cups are great for that. The new Yeti and Hydro Flask and Arctic type of double-walled insulated containers are great for that. All those things create what we call as a closed system or a really well insulated system. Now, here's one problem that we have with our equation. If we're gaining energy, that's positive. If we're losing energy, that's negative. So you can't have a positive equaling a negative. So really, when we do our math, we have to have another negative sign inserted here to make that happen. Okay? Now, using Q equaling negative Q isn't very useful for us. So instead, we want to measure masses, specific heat capacities, and temperatures. So we take what Q is equal to instead of equal the opposite of the other Q. Okay? So if I'm absorbing energy here and I'm losing energy here, the opposite will work for us. Now, what that means for us is because we are releasing energy, the final temperature here will always be smaller than the initial. All right? So this will always be negative. That meaning it's going to be negative. That's why we take the opposite of that, so two negatives will then equal a positive. On this side, we're always absorbing energy, so our temperature final will always be greater than our temperature initial. So as a result, we're going to have a positive side over here. Now, of all these variables that are inside of here, one of these variables will always be the same number, okay? We can have different masses. We're going to use two different substances, so we can definitely have, and we will normally have, two different specific heat capacities. The starting temperatures of both things can be different, and they should be different, otherwise this wouldn't be worth doing at all. But the one thing that's always the same, and I would mark this down in your notes, is that the temperature final for both things will end up being the same. So T sub F is the same on both sides of this equation because they're going to come to thermal equilibrium, which means they're going to have the same temperature at the end. Okay. Now, a scenario like this that would work, there's lots of little things. You know, blacksmiths use this when they cool down iron into water. Whenever you use a chemical hot pack, or maybe on a cold hockey game or football game, and you broke it open and stick it in your pocket, the energy that comes, the energy that is released from that hot pack, you want it to go 100% into your hands to keep your hands warm. Okay. In physics, we actually use this also to identify unknown metals. All right. So if we have a metal and we don't know what it is or what its purity is or what kind of alloy it is, we actually can do an experiment where we take a certain mass of it at a certain temperature and we will douse it in water. Okay. So what would happen is if the metal is on this side, a hot metal can then be doused into cold water, and if we put it in an insulated container, we can track the temperature changes. From that, we can find the specific heat capacity of that metal and then look it up on a chart or what kind of metal or what type of alloy that is. Right? That process I just explained is actually a standard chemical, or not chemical, physical, well, I guess it could be chemical too, lab called calorimetry. All right? We're basically studying the calories, or the joules in our case now, of the changes. Okay? So it's our methodology that we use. Right? Now in calorimetry itself, we're going to pull up this applet for us to see what kind of goes on here. What we have is we have an insulated container. Okay, we're going to have stirring that goes on here to keep it, flowing inside of here so we don't get hot spots or cold spots. And we're going to take a metal. All right, so let's pick any metal here. Let's just go with silver at our top here. Silver has a specific heat capacity in joules per gram Kelvin of 0.234. So since we talk about kilograms, this would be kilograms. This number would slide over, so it would be 234 compared to what we normally have been talking about. We're going to put a lot of mass in, so we're going to get a big chunk of our our silver, 120 grams, and we're going to start it off as hot as we possibly can. Now we're going to put it in 30 grams of water and at 20 degrees Celsius. Okay, so what should happen is as this really hot chunk of silver goes into water, the silver will lose temperature, the water will gain temperature. Okay, so let's see it happen. So we plug it in, we're stirring, we close it, we seal it, and we see as we measure the temperature, this is water's temperature now, right? It started at 20 to start. It increases, increasing until a point where we reach thermal equilibrium. Now, thermal equilibrium is a point at which they are the same temperature. At this point, we get a flat line, all right? Now, we don't see the change in the metal, but if we could, what we would have saw is the metal started at 220 degrees Celsius. So way up here above our graph, we would have seen this thing dropping in a linear fashion down to right here. And at that point, the metal would have also flatlined. Okay, so we're only seeing half of the information here, but that's the half that really matters, because as long as we know the starting temperature of the water and the graph tells us our final temperature, we have all the information we need to solve this. Okay. In your guys' lab, you'll be doing something very similar to this, where you'll be putting a hot metal into room temperature water, and we'll be tracking the starting point and that final temperature of our metals in here. All right. Now, if we reset this and do something like copper, okay, copper specific heat capacity is bigger than silver's. All right. Let's go to iron actually, because it's even bigger. If we do the same parameters than we did before and start this, we should see that this iron, being that it has a higher specific heat capacity, it can dump more heat energy into the water. So we see a much steeper slope, and we also see that as this thing grows, we're going to get a higher final temperature. Okay, so that goes back to the conversation we had the other day about what happens when you have high specific heat capacity versus low. High specific heat capacity has the ability to give the water more energy or to warm it up more. Okay, so that's just kind of an example, a little graphic here for us to look at in comparison to what we'll be doing in actual lab come tomorrow or the next day. Okay. Now, here's a practice problem for us to do in terms of calorimetry. In a desperate attempt to warm a bath, prospector heats up a gold nugget to 500 degrees Celsius, drops it into a bathtub with 55 kilograms of water at 24 degrees Celsius. What would that mass of gold need to be to heat the water? Okay, so set up your MCAT or your MC delta T equal to each other. Don't forget your negative, and let's solve it. Once you're done solving it, then hit play again on the video. So pause it now, and then we'll show you the answer. Okay, so you hopefully have solved it, and here we go. So we know that the water is going to be absorbing the energy. The gold is going to be releasing energy, so we set them up this way. And we have the mass of the water, we have the specific heat capacity of water, we know its starting temperature, its final temperature. We know the specific heat capacity of the gold, its final temperature, which is the same as water's, notice how they're both 39, and its starting temperature. Do the algebra, rearrange it, solve it, and we end up with 58.0 kilograms of gold. Okay, now that would be about 128 pounds of gold that you'd have to do to make this happen. Okay, that's actually pretty realistic considering water has a very high specific heat capacity and gold's is very low. So it's going to take a lot of gold to warm up a little bit of water. Okay, all right, guys, that is actually the unit. Thank you.